Atomic structure. Introduction. Atoms are the smallest particles of matter which are made up of three fundamental subatomic particles: protons, neutrons and electrons. Rutherford's atomic model. Rutherford's experiment. Rutherford bombarded a thin gold foil of thickness 0.00004 centimeters by alpha particles. The particles that emerged through the gold foil were allowed to fall on a ZNS screen where they produce glow and get detected. Observations. Most of the alpha particles passed through the gold foil without deflection. Some of the alpha particles were deflected through a small angle less than 90 degrees. A few alpha particles were deflected from their path through angle greater than 90 degrees. A very few alpha particles were deflected completely back by an angle of 180 degrees. Conclusions. The atom consists of largely empty space. The atom consists of a small positively charged massive part at its center. Volume of a nucleus is very small as compared to the volume of an atom. All the positive charge and almost all the mass of an atom is concentrated at the center of the nucleus. Rutherford's atomic model. On the basis of these conclusions, Rutherford proposed his model of an atom as follows. An atom consists of a compact, central, positively charged, massive core called as the nucleus. Almost entire mass of an atom is concentrated in the nucleus. Number of negatively charged electrons equal to the number of positive charges on the nucleus revolve in various orbits around the nucleus. Thus, Rutherford's atomic model resembles the solar system in which the planets revolve around the sun. Nucleus contains positively charged protons and chargeless neutrons. The atom is electrically neutral, hence the total number of electrons must be equal to the total number of protons. The electrons and nucleus are held together by electrostatic force of attraction. Drawbacks of Rutherford's atomic model. An electron revolving around nucleus should continuously emit radiation and lose energy, according to Maxwell theory of electromagnetic radiation. Due to this, the electron should come closer to the nucleus by following a spiral path and ultimately fall into the nucleus. Hence, this atomic model must be unstable. But this never happens. This model cannot explain the exact arrangement of electrons around the nucleus in various energy levels. It fails to explain the formation of line spectra by atoms of elements. Bohr's atomic model. Bohr modified Rutherford's model of atom, which explained the atomic spectrum of hydrogen atom and the stability of the atom. Postulates of the Bohr's atomic model. Electrons revolve around the nucleus in a definite concentric circular path called as orbits or energy levels, situated at a definite distance from the nucleus. As long as electron remains in a particular orbit, it neither emits nor absorbs energy. Thus, in a particular orbit, energy of the electron remains constant. These orbits are called stationary energy levels or stationary orbits or shells. These stationary orbits or shells are represented by capital letters K, L, M, N, and so on. Energy goes on increasing as stationary level goes further from the nucleus. A definite amount of energy is absorbed when an electron jumps from a lower energy level to a higher energy level. Similarly, a definite amount of energy is given out when an electron jumps from a higher energy level to a lower energy level. The energy absorbed or emitted is the difference between the energies of these two stationary levels and is given by Planck's equation. Heat energy is equal to E2 minus E1, which is equal to HV. E2 is the energy of higher energy level, E1 is the energy of lower energy level, V is the frequency of radiation, H is the Planck's constant. An electron can move only in that stationary orbit without radiating energy, for which the angular momentum of an electron is an integral multiple of h upon 2 pi. mvr is equal to n into h upon 2 pi, where m is equal to mass of electron, v is equal to the linear velocity of the electron, r is equal to radius of orbit, h is equal to Planck constant, n is equal to principal quantum number. 1 is equal to k, 2 is equal to L, 3 is equal to M, 4 is equal to N. Drawbacks of Bohr's model. It cannot explain the splitting up of lines in the spectrum of the electric field called as Stark effect and magnetic field called as Zeeman effect. It fails to explain the atomic spectra for elements containing more than one electron. It fails to explain the hyperfine spectrum. Shells, subshells, orbitals. Shells. Electrons revolve around the nucleus in a stationary energy level called orbit or shell or principal energy levels and are represented by n, which can have integral value 1, 2, 3 and so on, and can be represented by letters k, l, m, n and so on. The energy of the shell goes on increasing as the distance of the shell increases from the nucleus. Subshells or sublevels. Shell is further divided into subshells. These are S, P, D and F. The order of energies of various subshells for a given principal shell in the order of F is greater than D, is greater than P, is greater than S. The region in the three-dimensional space in which there is a probability of finding the electron is called orbital. Each subshell is further subdivided into one or more energy states called orbitals. Shapes of S and P orbital. S orbital. It is non-directional. It is spherically symmetrical around the nucleus. The size and energy of the s orbital increases with increase in the principal energy level, that is in the order 4s is greater than 3s, is greater than 2s, is greater than 1s. p orbital. The first shell K does not contain p orbital. The L shell onwards contains p orbital. The p orbital is dumbbell shaped, having two lobes on either side of the imaginary plane that passes through the nucleus. There are three orientations of the electron cloud in the p orbital along the axes x, y and z, namely px, py and pz. Px, py and pz orbitals of particular shell have the same energy. Orbitals are degenerative. The size and energy of p orbital increases with increase in the principal energy level. That is, 4p is greater than 3p is greater than 2p. The size, shape and energy of three orbitals is identical. Quantum numbers. Definition. The numbers which give a complete information regarding position of an electron, energy associated with an electron, orientation of an orbital and spin of electron in an atom are called as quantum numbers. They are as follows. The principal quantum number n, azimuthal, subsidiary, orbital quantum number L, magnetic quantum number m, spin quantum number s, principal quantum number n. This number indicates the principal or the main energy level to which the electron belongs. It determines the distance of an electron from the nucleus. It can have value 1, 2, 3 and so on. As the value of n increases, size of shell increases. It determines the energy of the orbital and it gives information about the maximum number of electrons that can be accommodated in a shell. Size of orbital increase with increase in principal quantum number. Azimuthal quantum number. It is also called as subsidiary or orbital or angular quantum number and is represented by letter L. It gives the shape of the orbital. It gives the subshell to which the electron belongs and the number of subshells present in the principal shell. The value of azimuthal quantum number depends on the value of principal quantum number of the shell. It can have a positive integer values from 0 to n-1. For example, when n is equal to 1, L is equal to 0 to n-1, which is equal to 0 to 1-1. Therefore, L is equal to 0. That is, there is only one subshell which corresponds to L is equal to 0. When n is equal to 2, L is equal to 0 to n-1, which is equal to 0 to 2-1, which is equal to 0 to 1. That is, there are two subshells which correspond to L is equal to 0 and 1. The subshells corresponds to the first four values of L is equal to 0, 1, 2, 3 are designated by letters S, P, D and F respectively. The energies of subshells are found to be in the following order. F is greater than D is greater than P is greater than S. The letters S, P, D and F originate from the term sharp, principal, diffuse and fundamental, which are used in the atomic emission spectra. Magnetic quantum number M. The magnetic quantum number indicates the spatial orientation of each subshell in an external magnetic field. For each value of L, M can have values ranging from -L to +L, including 0. The value of M depends upon value of azimuthal quantum number L. For each value of L, M may have L+1 value ranging from -L, 0 to +L. The positive value indicates orientation of the orbital in the direction of the magnetic field, and negative value of M indicates the orientation of the orbital in the direction opposite to the magnetic field. Under the influence of an external magnetic field, the electrons in a given subshell orient themselves in a certain preferred regions of space around the nucleus. These are called orbitals. Spin quantum number. It gives the direction of spin of an electron in an atom and is denoted by S. The electron in an atom revolves around the nucleus and also spins around its own axis. Spin of electron can be a clockwise or an anti-clockwise direction. Spin quantum number can have only two orientations having values of +½ or -½ If the spin is clockwise, it is denoted by +½ or by an up arrow. If the spin is anti-clockwise, it is denoted by -½ or a down arrow. Electronic configuration of elements. The distribution of electrons in various shells, subshells and orbitals of an atom is known as an electronic configuration. The distribution of electrons in the various subshells and orbitals of the outermost shell of an atom is called valence shell configuration. Electronic configuration is mainly explained by the following rules. Aufbau principle. Aufbau means building up. This principle tells the sequence in which various orbitals are filled with electrons. It states that in the ground state of the atoms, the orbitals are filled with electrons in order of the increasing energies. The order of increasing energies of the various orbitals are as follows. 5f is greater than 7s, is greater than 6p, is greater than 5d, is greater than 4f, is greater than 6s, is greater than 5p, is greater than 4d, which is greater than 5s, which is greater than 4p, which is greater than 3d, which is greater than 4s, which is greater than 3p, which is greater than 3s, which is greater than 2p, which is greater than 2s, which is greater than 1s. Hund's rule of maximum multiplicity. When several orbitals of the same energy are available, the electron first fills all the orbitals singly with parallel spin and then pairing starts with the opposite spin. The configuration of 4 electrons occupying the p orbital is as shown below. For example, carbon, atomic number 6, 1s2, 2s2, 2p2. Nitrogen, atomic number 7, 1s2, 2s2, 2p3. Oxygen, atomic number 8, 1s2, 2s2, 2p4. Pauli's exclusion principle. It states that 2 electrons in an atom cannot have the same set of 4 quantum numbers, or only 2 electrons may exist in the same orbital with 3 quantum numbers same. That is, the 4th quantum number is different and these electrons must have opposite spin. See the example given below. The anomalous behavior of copper and chromium. Chromium, atomic number 24. Expected configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Actual configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Inter-electronic repulsion forces one 4s electron to enter into 3d orbital to make 4s and 3d orbital half filled, which gives extra stability to the chromium atom. Cu, that is copper, the atomic number being 29, the expected configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. The actual configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Inter-electronic repulsion forces one 4s electron to enter into the 3d orbital to make it completely filled and 4s orbital half filled, which gives extra stability to the copper atom. The table showing the electronic configuration of elements with atomic number 1 to 30 is shown below.